Okay, so picking up where we left off last time, we had just introduced ASTC, All Students Take Calculus. What we're going to do now is we're going to derive and revisit the sort of classic angles that we might have encountered before. So during the last lecture, in section 4.1, we introduced very common angles. We had 30 degrees, 60 degrees, some 45-degree angles, and then we had a whole bunch of pizza slices that we were trying to understand and represent a little bit. So a perfectly valid question you might ask is, why those angles? Why did we bother coming up with those in any way? Well, there's a couple of reasons. One is they're naturally divisors of 360, which is our agreed upon full revolution of in the measurement of degrees. But what's actually more relevant for why they're our favorite angles is because they come from the most natural of objects. So what we're going to do here is we're going to derive how we can come up with what we're going to call the 30, 60, 90 triangle. This is going to be a right triangle that has 30, 60, 90 as its inside angles, and since one of them is a 90, we know it's a right triangle, which means that we can figure out the sine, cosine, and tangent of 30 or 60 by referencing this right triangle. So where does this come from? Well, there's a couple ways you could go about creating it. The way I like to go about creating it is as follows. We're going to start by generating an equilateral triangle. And so over here to the right, we're going to build an equilateral triangle. Equilateral, of course, means equilateral. This means equal-sided. So we can choose this triangle to have the same side lengths. Maybe we'll have those side lengths be 2. Now, a fun fact from geometry is that if you have a triangle with equal side lengths, then the measure of their angles, their interior angles, are necessarily all equal as well. So what that means is that if the sum of the angles of a triangle is always 180 degrees, then that means one of these angles, say alpha, has to be equal to 180 degrees over 3, which is 60 degrees. But all these angles are the same. So if that alpha is going to be 60 degrees, this angle is 60 degrees, and the angle all the way up here is 60 degrees. Now what we're going to do is we're going to cut this triangle in half. We're going to cut right down the middle like that. When we do that, we'll find that down here in the bottom, the base length that was a 2 just now got cut in half, so each side here is a 1. The hypotenuse to the right here is still a 2, but the angle up here, which was a 60, just got cut into 2 pieces, and those pieces are each going to be 30 degrees. Since we cut this triangle in half and we built a perpendicular altitude, what that's going to mean is that this angle right here is going to be 90. And with this construction, what we've now just done is we've taken an equilateral triangle, and if I take just this half of the triangle and I go ahead and recreate it over here, what I've just built is I've built a right triangle with a 90 degree, a 60 degree, and a 30 degree angle inside. So this is our 30, 60, 90 triangle, and the hypotenuse was a 2 and the base was a 1. So you now might ask, what's the height of this triangle? That is, what's the magic value that goes there? And this is where the Pythagorean theorem comes in clutch. Because if we call this our missing height, I don't know, call it y, then what we know is that y squared plus 1 squared is equal to 2 squared. That's the Pythagorean theorem. And that will imply then that y squared is equal to 4 minus 1, which is 3. And therefore, once we take the square root, we get y equals the square root of 3. Note, by the way, that although we took a square root, we're not going to get positive or negative because these are physical distances, and physical distances cannot be negative. So it turns out that this missing height for the 30, 60, 90 triangle is exactly a square root of 3. Now, oftentimes when students first encounter this triangle that we just built here, our favorite 30, 60, 90 triangle, this is something a lot of students choose to commit to memory. And that's not necessarily a bad approach. Although I don't like recommending memorization, for trigonometry there does have to be a minimum amount of memorization. Oftentimes students don't want to have to recreate it using this equilateral triangle, so they just opt to memorize it. If you do choose to memorize this, note that the minimum amount you have to memorize is that the side lengths involve a 1, a 2, and a 3. You need to memorize that the 2 is always the hypotenuse. And then you should remember, this is the way I think of it, that the square root of 3, the 3 goes with the 3. So the square root of 3 is adjacent to the 30 degrees. And then, of course, the 1 side length goes in the only spot that's missing. However you choose to memorize this, feel free to build out your own approach. I'm definitely going to use the 3 goes with the 3. So you'll probably hear me use that in the future. So this triangle helps us understand if we have a 30 degree and a 60 degree angle inside of our right triangle. This helps us understand what the hypotenuse and what the side lengths of this triangle might look like. Now what we're going to want to do is we're going to want to do the same exact thing, but somehow figure out what's going on with 45 degrees, because that was another interesting angle in our pizza slices during the last lesson. To do that, we're going to have to, instead of looking at an equilateral triangle, we're now going to have to look at the square. If we build a square and we choose the square to have a base length of 1, and therefore, since it's a square, its height is also 1. And now we choose not to cut it straight down the middle, but instead cut the square diagonally. What we'll find is that, well, of course, it's a square, so all of its interior angles are 90 degrees. But now, this 90-degree angle that we had all the way up here, as well as the one we had down here, just got cut in half by this diagonal. So what that means is that this interior angle is going to be half of 90, which is 45. And again, this angle down here is 45. So just like we did last time, we're going to take this triangle right there, and we're going to port it over into its own triangle over on the right, where this triangle is going to be a triangle with 90 degrees and 45-degree acute interior angles. The base and the height are both 1, and so if you want to know the missing hypotenuse, again, the Pythagorean theorem kicks in. We know based on the Pythagorean theorem that h squared is going to be equal to 1 squared plus 1 squared, but of course that's just a 2. And so that tells us then that h is equal to the square root of 2. Again, how you choose to learn this reference triangle is up to you, but this is going to be our 45, 45, 90 triangle. Arguably, everything we've talked about so far is literally enough to get started with trigonometry. You need your 30, 60, 90 triangle, your 45, 45, 90 triangle. You need to know how to find reference triangles given any angle. And then from there, you just need to know whether sine, cosine, tangent are positive or negative, and whether the sine is opposite over hypotenuse and the cosine is adjacent over hypotenuse and the tangent is opposite over adjacent. Literally all that information is enough to get you where you need to go in trig. So what we're going to do now is practice a little bit and see if we can't sew all this information together in a way that makes going through examples make a little bit more sense. Now, I mentioned when we started this lesson that the textbook is going to do this in a slightly different way, and that still holds true. All the content that we've learned so far is really not talked about until sections 4.3 and 4.4, which is somewhat interesting to me. Again, not necessarily a wrong way to do it, but I think that there are better ways to organize this information. What we're about to do a series of examples that in the textbook would not have been done until 4.4, to give you an idea of where we're at right now. These are going to be computing sine, cosine, tangents, cosecants, secants, and cotangents of arbitrary angles. This is the most important part of this lesson. Being able to be given any angle we want and then determine what its trig value is going to be. The way to do this is you start by graphing the angle in question. You then find its reference triangle. Once you find its reference triangle, you need to then figure out the sides of that reference triangle and then use that to evaluate the angle at the given indicated trigonometric function. So it's a little bit of a process. I will warn you that if you are a person that has memorized all of this stuff in a past lifetime, you will not be able to just regurgitate an answer. It is imperative that you demonstrate how you get the answer and that you understand the underpinning and the background argumentation for these trigonometric problems. So for example, here we have sine of pi over 6. So that means the angle in question, pi over 6, we might recall that that's 30 degrees. So I'm going to draw a picture of 30 degrees. We know that lives right there. That is going to be 30 degrees. We also know that this is in quadrant 1. So that means we're in the A quadrant of ASTC. So that means sine, cosine, and tangent are all positive. If we draft now the reference triangle that we want to build, that's going to be a triangle right here in orange. But once we built that, we now want to ask ourselves what the base, the height, and the hypotenuse are. But what we recognize is that since the innermost angle is 30 degrees, this is a 30, 60, 90 triangle. So right off the bat, we know what x, y, and h are. We know that x is going to turn out to be square root of 3 because it's with the 3. The y here is a 1 and the h is going to be a 2. So what that means is that sine of pi over 6 is going to be, remember the relationship of the sides of the triangle for sine, SOHCAHTOA, we know sine is going to be opposite over hypotenuse. So in this case, it's going to be y over h, which is 1 over 2. So again, just to reiterate the process here, we started with sine of pi over 6. We drew a picture of that angle. We built the reference triangle. We filled in the data for the sides of the reference triangle. We then figured out what the sine of that reference triangle is. It was 1/2. And then we used the ASTC, all students take calculus, in order to verify for ourselves that indeed, okay, sine is positive. Good. So let's take a stab at that again, but with a different angle. Here we have cosine of pi over 4. Again, you might note that theta in this case is pi over 4, which, if it makes it easier for you, is 45 degrees. So we're still in quadrant 1, but now this is our angle, where this angle is 45 degrees. The reference triangle we build is going to be dropped down to the x-axis, so I know that that's going to look something like this, where we have a right triangle. Then we still have a base, a height, and a hypotenuse, But now we recognize that this triangle, this reference triangle, is a 45, 45, 90 triangle. So the base here is 45, not 45 degrees. The base here is a 1. The height is a 1. And the hypotenuse is the square root of 2. And therefore, cosine of pi over 4, we remember that cosine is adjacent over hypotenuse, so that's x over h, and here we're going to get 1 over square root of 2. We might confirm for ourselves that here we're still in quadrant 1, so just like we were before, we're bound by the A part of all students take calculus, and the A part tells us that our answer should be positive, which it is. So that means we've done everything correct. Now, you might, based on a past lifetime, by the way, this was adjacent over hypotenuse, you might, based on a past lifetime, feel compelled to rationalize 1 over square root of 2. There's no reason why you should feel compelled to have to rationalize things. Again, just like we've discussed in the past, a number is a number. It does not really matter how it's represented. You should know how to rationalize something, but you shouldn't feel compelled to do so, because there's not really a good reason for rationalizing every single thing you see. This is a perfectly fine final answer. Now, if you do choose to leave your answer as, say, root 2 over 2, because you rationalized it, fine. But if all you did was memorize these answers and your memorization says cosine of pi over 4, boom, has to be a root 2 over 2, and you don't provide any of this justification, I'm going to be hard-pressed to understand that you actually know what's going on. The next example has us take a look at the tangent function. Just like we did before, we're going to graph the angle, where the angle here now is theta is pi over 3, otherwise known as 60 degrees. And so here, we're still in quadrant 1. Here's 60 degrees. So we're still in quadrant 1. So again, we're bound by the A part of all students take calculus. So our answer should be positive. The reference triangle that we want to build will have its hypotenuse on the terminal side of the angle. It'll have its base on the x-axis. There's our right triangle. It will have a base x, a height y, and a hypotenuse h, where now we again recognize this as a 30, 60, 90 triangle, but the inside angle here is a 60. So the way this is going to differ from the first problem that we encountered is that the y and the x values are actually going to swap. So in this case, again, 30 goes with the 30, and the 1 goes with the 60. So the x here is now a 1, the y is a square root of 3, and the hypotenuse is a 2. So that now, if we want to compute, say, the tangent of this angle, remember that a tangent is opposite over adjacent. So here we're going to get y over x, which is the square root of 3 over 1, which simplifies into the square root of 3 if you so choose it. It's again positive, which matches our quadrant that we lived in. So all in all, this is a sort of soft introduction here of how to compute sine, cosine, and tangent of the angles that we're starting with. But these angles are all things that we are familiar with based on the last lesson. 30 degrees, 45, 60, these are all very common. And that's because they were all putting us in quadrant 1, and so everything sort of feels like it's nice and ready to go. But there's no reason that has to be the case. As we saw earlier in this lesson, your angle can be outside of quadrant 1, and this is going to produce reference triangles that are going to live in different quadrants, which means the sine, cosine, tangents are going to now start flipping to negatives, potentially. Let's take a look at a couple of those examples, and maybe we'll see what I mean. Let's jump to number 6 here, the secant of 3 pi over 4. So you might recognize that 3 pi over 4 If you want to convert that to degrees, you can, but we do need to get comfortable with recognizing their radian representation. So at the very least, what you should recognize here is that 3 pi over 4 lives in the second quadrant. That is the angle 3 pi over 4. What that means is that the angles living inside quadrant 2, and so again, by all students take calculus, this is the S region. So what that means is that sine and its reciprocal cosecant will be positive, but everything else will be negative. In particular, cosine and secant will be negative. And so with any luck, as we build our reference triangle, we will get a negative result when we compute a secant. Let's build out that reference triangle. Again, we're going to do that in a different color. The reference triangle for quadrant 2 drops down to the x-axis like this. And there is our right triangle. Our right triangle is going to have a base, x, a height, y, and a hypotenuse, h. But now comes the real question, which is, what's that angle? What is the interior angle of this triangle? Well, this is where you have to do a little bit of math in order to make this make sense. Notice that this angle is 3 pi over 4, but remember that a straight angle is the full half turn. The full half turn is 180, otherwise known as pi. So if I call this angle in here alpha, we might observe over here that alpha plus 3 pi over 4 is of course pi. That's the full half turn. So if I solve for alpha, alpha is going to be pi minus 3 pi over 4, which is going to be pi over 4, otherwise known as 45 degrees. So now alpha is well known. Alpha is 45 degrees. What that means is that this reference triangle is now magically a 45, 45, 90 triangle. As soon as we know that it's a 45, 45, 90 triangle, we can fill in the missing sides. We know that the base has to be a 1, the hypotenuse is a 1, the height is a 1, and the hypotenuse is a square root of 2. Now, if you so choose, you could be careful about the fact that in this case, since we're in quadrant 2, this x value is moving into the negative xward direction, and this is what caused, via the all students take calculus, this is what's causing sine to be the only positive trig function. And so one way you can sort of integrate the positive and negative check is you could realize that x here, you could write this as a negative 1 if you so chose. You can either write that as a negative 1 and then you don't have to do the all students take calculus, or you can leave it as a positive 1 and do the all students take calculus. Or, my preferred option, do both and verify that they get the same answer, because that way you can check your work. Now, what you might recall is that secant of 3 pi over 4 is the same thing as 1 over cosine of 3 pi over 4. And so where cosine might have been adjacent over hypotenuse, the secant is then going to be the reciprocal of that, and so that's going to be hypotenuse over adjacent, hypotenuse over adjacent. And so this would end up being h over x, which in this case is the square root of 2 over negative 1, which is the negative square root of 2. And so we recognize that the answer at the end of the day was negative, which matches the fact that only sine was supposed to be positive, and therefore the secant and the cosine were negative. This is the main idea for how we can find a trig function like secant of an arbitrary angle like 3 pi over 4. Notably, the angle related to the reference triangle has to now be deduced by using some sort of a computation involving the other angles around it. So that's the new twist on what we're doing. Now, I skipped 2 problems up here because these problems have angles like, in this case, the angle is pi, otherwise known as 180 degrees. And in this angle, we have theta is negative pi over 2. These are special angles because when you draw them, they don't live in any one quadrant. They live on sort of the boundary of 2 different quadrants. And so what that means is either the height or base, the y or the x of the corresponding reference triangle is going to be 0, which is somewhat interesting and a little weird at the same time. So for example, with pi here, what we end up building is we have our angle that starts over here on the positive x-axis. It goes all the way to the left, and it builds out an angle over here. So what would the reference triangle be? Well, if the angle, as we saw in this example here, if the angle ended somewhere in quadrant 2, this would be the reference triangle. So if the angle, for example, would have ended here, we would have built that triangle. If the angle would have ended here, we would have built that triangle. If the angle would have ended there, we would have built that triangle. And what you see is that actually the angle is ending all the way down here on the x-axis. So the triangle we're building has heights that are getting smaller and smaller and smaller and smaller. This develops what is called a degenerate triangle. It's a triangle, however, the height that you're concluding, there's the y value, there's the y value, there's the y value. This y value is actually going to 0. And that once we finally get to 180 degrees, the reference triangle that we're building is actually going to look something like this. It will almost look like you can't even see it. It'll just look like this angle to the left. So again, this is our straight angle. The reference triangle, which I've been drawing in orange, will literally just look like this. I mean, that doesn't look like a triangle at all, but it is a triangle. But the point is that we're ordinarily, again, we'd still have x's and h's and y's. Here, the y value is actually 0. The h's, which we saw were the hypotenuse, right? The h's and then the bases, which were down here. Observe that as our triangle is moving further and further down to the x-axis, the h's and the x's actually start getting very close to one another. So in all actuality, the h and the x are the exact same value. However, what we noted on the previous page is that the hypotenuse is always taken to be positive, and in this case, the x is clearly extending in the negative direction, so the x is negative. Additionally, since all of this is being done on a unit circle, we're going to agree that the hypotenuse is always a 1. So therefore, at the end of the day, this h is going to be a 1, this x is going to be a 1. The x, of course, not really a 1 necessarily. The x is going to be a negative 1. And so, as a result, if I wanted to find cosine of pi, cosine by its trigonometric relationship is adjacent over hypotenuse. So that's going to be adjacent over hypotenuse. And so we're going to get x over h, which is negative 1 over 1, which is negative 1. Now, this concept is a little bit difficult to understand in the beginning, this whole notion of a degenerate triangle. And admittedly, you're allowed to be a little bit frustrated with the idea that x and h are basically the same thing, but one is positive, one is negative. Again, this goes back to the way we've defined the notion of a hypotenuse and the way we've defined the notion of a reference triangle. But as long as we agree with these notions and these definitions, this is going to be our agreed upon evaluation for cosine of pi being -1, and this turns out to be the correct way to do it. We can do the exact same game here, but we can do it with, instead of a horizontal angle like that, we could do it with a vertical one. So for example, here we have -pi/2. We can graph that. Again, we start in the positive x-axis direction. Negative means we're going to be sweeping clockwise, and pi/2 is, of course, that's -90 degrees, so we're going to end up down here. And this becomes our angle. So what is the reference triangle? Well, again, the reference triangle is sort of living in this strictly one-dimensional space right here, this vertical line. So what's really happening is that, if our angle had been, say, right there, that would be our reference triangle. If the angle was right here, that would be our reference triangle. If the angle was right here, that would be our reference triangle, and so on and so forth, where we recognize that as these start sweeping, we see then that the widths, which now I'm going to highlight in yellow like we did before, this is going to be the width of the first reference angle. This is going to be the width of the second reference angle. This is going to be the width of the third reference angle. And what you see then is that each of these widths, which the first one is x, the second is still x, the third is still x, as my reference triangles move in this counterclockwise direction, these widths are getting tinier and tinier and tinier. And so what we see in this case is that these x values are actually going to 0 as I move toward -90 degrees. And so what that means is that the reference triangle I build, if I build it out over here to the right, again, we start over here, we end up over here. The reference triangle I build is just this boring straight line pointing straight down, where just like I did before, I'll recognize that there's still technically a height here, and there's still technically a hypotenuse. There's still technically a width, although we saw that the width is 0, just like above, the height was 0. And so x is equal to 0. The y, again, is going to be equal to, well, it's pointing downwards, so that's negative. We're going to agree that since all this is occurring on a unit circle, these h's are going to be 1s. So the y here is equal to -1, whereas the h is equal to a positive, because as we noted over and over again, here x is 0, y is negative, and h, the hypotenuse, is always positive. So as soon as we have sort of this information about what's going on at -90 degrees, we can now turn around and say, oh, okay, cool. Maybe we'll come down here to the bottom left and we'll say that the tangent of -pi/2 is going to be opposite over adjacent, where the y is a -1, the adjacent is a 0. This is going to be a problem. We've put in all of this work to try to get this far, and what we just ended up with is a glaring issue. This is a problem. You can't divide by 0. This doesn't make any sense. This is a failed answer right there, because you can't divide by 0. So what we've actually just concluded after going through all of this rigmarole is that the final answer that we're going to come up with here is that this is undefined. Now this is actually going to be fairly common because sine, cosine, and tangent all have quotients, meaning they have things inside their denominators. The tangent will have will have an x in its denominator, the cotangent will have a y in its denominator, and therefore there are opportunities for undefinedness to pop up. If you memorized some sort of a trig chart in a past lifetime, you might remember this occurring. But it's important, again, as we move forward, for us to know why this is happening. What is this justification for what's occurring? So hopefully this is making a little bit more sense as we do more examples. So now what we're going to do, we've taken a look at some degenerate triangles, we looked at some undefinedness, we did one involving a secant. What we have here are two examples involving a cotangent and a cosecant. So let's take a look at those and see what those are going to be equal to. For cotangent of 11 pi over 6, I'm not going to convert that to degrees because, again, we need to get more comfortable moving forward. 11 pi over 6, we should know where that lives. That lives right here in quadrant 4. So our angle is that angle. That's 11 pi over 6. The reference triangle that I build for this is going to then make some sort of a right triangle with the x-axis, where I have a base, a height, and a hypotenuse. What is the innermost angle here? Well, that innermost angle, which I might call alpha, again, we have to figure that out. Alpha seems to be a full revolution without this sort of partial revolution, which is 11 pi over 6. Quick math tells you that this is pi over 6. So this angle, which by the way is 30 degrees, so this angle is 30 degrees, meaning that the triangle we're looking at is a 30, 60, 90 triangle. What that means is that the x value adjacent to 30 is going to be square root of 3. The y value opposite of 30 is going to be equal to a 1, and the hypotenuse is a 2. But you might remember that y here is extending negatively, so that's going to be a negative 1. And so if we wanted to compute the cotangent of 11 pi over 6, this is going to be the same as 1 over the tangent of 11 pi over 6, which means if tangent was opposite over adjacent, cotangent is adjacent over opposite, which in this case is the square root of 3 over negative 1, which is going to be negative square root of 3. And then you might recall that we have all students take calculus, and so what that means is that cosine is the only thing that's allowed to be positive, and since we're computing tangents, negative is the correct way to go. The next example has us taking a look at a cosecant. Here we have negative 4 pi over 3. So if we were to draw negative 4 pi over 3, that's going to live in the second quadrant because the angle is negative, which means it's sweeping in a clockwise direction. 4 pi over 3 is just a little bit larger than pi, so that means we sweep like that. This is negative 4 pi over 3. So that means that the reference triangle that we build is going to have that for its hypotenuse. Then it's going to have a height and a base, where the base is x, the height is y, the hypotenuse is h again. And the question is, again, now, what is this reference angle? Well, we're going to call that alpha like we usually do. And what we recognize is that that alpha is going to be the magic alpha such that alpha plus pi has to be equal to 4 pi over 3, which implies that alpha is equal to 4 pi over 3 minus pi, and therefore that's equal to pi over 3, otherwise known as 60 degrees. So what that means is that this alpha is a 60-degree angle, meaning we have another 30, 60, 90 triangle on our hands, where the opposite angle to that is going to be the 30 degree. So we know y here is going to be square root of 3. The x here is going to be a -1 because we're extending in the negative direction. And the hypotenuse is a 2, which means based on this information, the cosecant of -4 pi over 3 is going to be equal to 1 over sine of -4 pi over 3. If sine was going to be opposite over hypotenuse, then the cosecant is going to be hypotenuse over opposite. And so in this case, we end up with h over y, 2 over the square root of 3. Or again, I'm not going to rationalize the answer, no need for that. And additionally, we might realize that if we do the mnemonic device ASTC, living inside the second quadrant means that sine and its counterpart cosecant should be positive, and we recognize that our answer is positive. So hopefully this is making a little bit more sense in how we go about solving trig functions of arbitrary angles. The next page has us tackling a whole host of additional examples. No, it does not. So hopefully this makes a little bit more sense and brings clarity to evaluating trig functions of arbitrary angles.